And good afternoon, everybody. Here's part 2 of your notes for section 3.2, and it's going to be a few more examples on proving trigonometric identities to be true. So the big idea for proving is that you want to make the one side, the left or the right side, equal to the other side. So here's our example. This is going to be a technique that you can use when you have equal fractions. And if you have one fraction equal to another fraction, what you could essentially do is multiply something that you need into one fraction that is in the other fraction. So for example, if I want the right side, if I want this side to end up looking like this side, well, what do you need for it to look like the other side? Well, for example, you're going to need a 1 minus sine squared, or 1 minus sine alpha, excuse me. You're going to need a 1 minus sine alpha to show up in the fraction over here on the right side. So what I'm going to do is just multiply in what I need and then follow the algebra from there. So for example, I'm going to take my original right hand side and multiply it by 1 minus sine alpha top and bottom. So we're going to have cosine of alpha and then 1 minus sine alpha, and then we have 1 plus sine alpha all over cosine alpha. And what I'm going to do is multiply the bottom by 1 minus sine alpha. And the reason I'm doing that is because I need it to end up looking like this one over here. Remember, for a proof, you can only change one side. So we're just going to change the right-hand side by multiplying by 1 minus sine alpha down bottom. And whatever you do to the bottom, you're going to have to do to the top to keep the fraction balanced. And that's going to get us to this step. So on the left, we still have our cosine alpha over 1 minus sine alpha equals, if I multiply these two binomials together, you're going to get 1 times 1, which is 1. This is a difference of two perfect squares pattern, since you have a plus and a minus, so it's going to be plus sine alpha and minus sine alpha, and those are going to cancel. So if you were to actually do that out, let's just do that off to the side if you're not able to do that in your head. So you're going to have a 1, and then you're going to have a plus sine alpha minus sine alpha, and then a sine times sine is a sine squared, so it's going to be minus sine squared. So these are going to cancel in the middle. So what you're basically left with is 1 minus sine squared alpha. So up top we have a 1 minus sine of alpha squared over, and down bottom we're not going to multiply the cosine into that binomial, we're just going to leave them separate. So we'll say this is going to be cosine alpha and 1 minus sine alpha. And the reason this is going to help is because if we look at our numerator, 1 minus sine squared, we know from our Pythagorean identities that sine squared plus cosine squared is 1. And if we bring our sine squared to the other side, then cosine squared must be equal to 1 minus sine squared. So the 1 minus sine squared that we have in the top of our fraction, we can just replace it with a cosine squared. So we're now going to have cosine squared up top. Over cosine alpha. And 1 minus sine alpha. And we're still equal to our left side. Cosine alpha. 1 minus sine alpha. And now we can go ahead and simplify our fraction a little bit. So we have two factors of cosine up top. It's cosine squared, so it's basically cosine times cosine. So you could think of it as this. So let's erase this. Cosine squared is the same thing as cosine alpha multiplied by cosine alpha. And we know that anything divided by itself is 1. So one of these cosines will cancel one of these cosines. And now we're equal to our left-hand side. Notice we have a cosine up top and a 1 minus sine alpha down bottom. So your last step would be just to rewrite that. So we're going to have the cosine alpha over 1 minus sine alpha equals, and then rewrite the right-hand side, and it's now identical to the left-hand side. So that should be our proof. This type of, I guess, thinking or side work doesn't need to be in the body of the proof. This can just be, kind of some side notes as far as where things are coming from. So the actual proof, if you were to number all the steps, so this would have been step 1, step 2, step 3, and this is step 4. So this ended up being a 4-step proof to show that the left side is equal to the right side. And let's go ahead and look at the next example. So this one, the technique is going to be separating one fraction into two. So if you have a common denominator, which in this case is sine x, you can split it into two separate fractions. So we can say it's going to be cosecant of x over sine x minus sine x over sine x equals cotangent squared. So for example, what you're basically doing here is if I had something like 3 plus 7 all over 7, you could split it back to the two fractions that it came from, 3 sevenths plus 7 over 7. So we're just kind of taking a step back as far as using that common denominator and writing two separate fractions. And once we have the fraction split, we can go ahead and look to simplify. So we know that sine is the reciprocal of cosecant. So on this first fraction we have cosecant of x. And then this is 1 over cosecant. Minus sine over sine, we could probably simplify that to 1, equals cotangent of x squared. And then if you have cosecant divided by 1 over cosecant multiplied by the reciprocal, that's going to get you cosecant squared. My mouse is not cooperating with me today. So there's cosecant squared minus 1 equals cotangent squared. And this has kind of the parts and pieces of one of our Pythagorean identities. So we know 1 plus cotangent squared is equal to cosecant squared. And if we rewrite this, if we brought our 1 to the other side, it would read cotangent squared is equal to cosecant squared minus 1, which is what we have on our left-hand side. So cosecant squared minus 1 can be replaced with a cotangent squared. And now we have the left side equal to the right side. So there's our proof. And let's see, how many steps was it? So there was step 1, step 2, step 3, and final step 4. So there's our 4-step proof to prove that the left side is equal to the right side. And let's go do the last one. So this one is adding or subtracting fractions. In this case, we're actually subtracting. So just like regular fractions, in order to add or subtract fractions, you need a common denominator. So we're going to need to get a common denominator. So on the left side, we will keep it 2 tangent of x squared equals, and let's set up our two fractions. We have a fraction minus another fraction. So a common denominator is going to be a denominator that represents all the factors in the original denominators. So we need to represent this factor, cosecant of x minus 1. So we need to represent cosecant of x minus 1. And I can already see I'm not going to have enough room, so let's erase this second fraction for the moment. And we'll make this one longer. Minus. And then the other fraction needs to have that same factor, cosecant of x. So we'll go cosecant of x minus 1. And it also needs to have a factor of cosecant of x plus 1. So cosecant of x plus 1. And now that we have a common denominator, now we need to adjust the numerators. So if we look at the first fraction, what did we need to multiply into the bottom? We had to multiply in a factor of cosecant x plus 1. So we need to multiply the top of the original fraction by the same thing. So 1 multiplied by cosecant of x plus 1 is cosecant of x plus 1. And what about the second fraction? What do we multiply new into that one? We multiplied in a cosecant x minus 1, so we need to multiply that into the numerator, so cosecant x minus 1. And there's our new fractions with a common denominator. And now we can go ahead and keep working the proof. So the left side is going to stay 2 tangent of x squared equals, and what can we do now that we have a common denominator? We can go ahead and add or subtract the fractions. So in this case we were subtracting. So cosecant x plus 1 minus cosecant x minus 1. So we know that cosecant minus cosecant would just be 0. And then we have a 1 minus a negative 1. So if you have 1 minus negative 1, two negatives in a row, that's going to make it plus. So we're basically going to end up with a value of 2 up top. So that's going to be 2. So cosecant minus cosecant was 0, and 1 minus minus 1 is 2. And we're probably going to need to, well, let's just put it over this. This is our first one. Let's not do too many steps at once. So cosecant of x minus 1, and then cosecant of x plus 1. So now we have 2 over that common denominator, and then we could multiply together those binomials in that common denominator. So let's say the left side is 2 tangent of x squared equals, we have a 2 up top, and if we multiply together these two binomials, we should get cosecant of x squared. You're going to get a negative cosecant and a positive cosecant in the middle, since we have that difference of two perfect squares factoring pattern. And then on the end, you're going to have a negative 1 times a 1, so negative 1. And then cosecant x minus 1, we actually saw that in the earlier problem. Not sure if it's still there. Yep, so cosecant x minus 1, we said that's the same thing as cotangent. So we can say we have a 2 tangent of x squared equals 2 over cotangent squared. So cosecant of x squared minus 1 is identical to cotangent. Cotangent is 1 over tangent, so that gives us 2 tangent of x squared equals 2 1 over tangent squared. And if you're dividing by a fraction, that would be the same as multiplying by the reciprocal. So on the left, 2 tangent of x squared equals, multiplied by the reciprocal, that's going to be 2 tangent of x squared. And now we have the left side equal to the right side. And again, if it's a good proof, it should be just going one step at a time. And you should be able to go through and number all the steps, preferably going vertically. So this would be step 1, step 2, step 3, step 4, step 5, and step 6. So that was a 6-step proof to prove that the left side is equal to the right side.